We're going to go through the solutions for the second part of our mole review, which is going to cover density, molarity, and stoichiometry, all in quite a condensed form. I'm going to try to go a little slower than I did in the last video. I felt like I was going a little fast. I was a little under the gun time-wise, to be honest. So I'm going to try to go at a more leisurely pace, maybe explain a little bit more of my thinking as I go. All right. So the first thing we did before we got started, this happened in class, is we took note of the different types of conversion factors that we might experience and need depending on, I guess, the situation. Now, in the last package, we looked at the mole and molar mass as molar quantity, or pardon me, as conversion factors. Things that allow us to convert from one quantity to another. In the case of the mole, that'll convert between moles and atoms, or maybe moles and particles, moles and molecules, or molecules. You get the idea. And the conversion factor for the mole is pretty simple. It's our Avogadro's number, 6.02 times 10 to the 23 things, and you can choose, pick your poison. Maybe you're talking about atoms. And that is all over 1 mole. Or maybe you want to choose the opposite conversion factor. You want to flip it. It's the same statement. Now, a key idea about conversion factors that we didn't have time to talk about in class is that the reason we're allowed to just multiply a value by something, as we do with conversion factors, is because each of our conversion factors has an equal value on the top and on the bottom of a fraction. And in other situations where you've seen fractions like this, where you have the same value on the top as they're on the bottom, well, that's equal to 1. So if I multiply some number by a fraction with the same value on the top and the bottom, well, what happens? I get 5 times 4 over 4. Okay, I'll go the long way around through this. So 5 times 4 is 20. So I get 20 over 4. And that simplifies. 4 into 20, it goes in 5 times. So in other words, by multiplying by a fraction, it's the same on the top as it is on the bottom, we're not fundamentally changing the value at all. Now, I'm just really changing the way I'm expressing it. So instead of saying a mole, I'm saying 6.02 times 10 to the 23 things. But those mean the same thing. They're the same value in the same way that 4 over 4 is a value. All right. We also, in the last package, talked about molar mass as a conversion factor, and that might look something like, I'm going to use, I think we use oxygen as an example in class, so that'd be 16.0 grams per mole, 1 mole. And that changes between mass, which is measured in grams, and moles. Or maybe you don't like that one, maybe you want to flip it because that's more appropriate for your conversion. That's fine too. Moving on, density. Density converts between mass and volume, or as a conversion factor, it allows us to do that. Density is actually a measure, a ratio, how much mass something has for the amount of volume it takes up. All right, so we can say, what should we use? What is the density that I know off the top of my head? I think nickel has a density of 8.9 grams per milliliter, per 1 milliliter. Or you could flip that. Maybe it's more useful to say every 1 milliliter of nickel occupies 8.9 grams. That's an example, just like oxygen is an example of density. Molarity converts between moles and volume. And so molarity, remember, is capital M, which means really moles per liter. So we'll do an example. Let's say I know that, let's not get too technical. Let's just keep it simple. So we could have a 0.200 molar solution, which would mean you have 0.200 moles of some solute for every 1 liter of fluid. Or you could express it as for every 1 liter of your solution, that occupies 0.2 moles of your solute. We also talked about molar volume. Now there's this specific idea that sometimes comes in handy that gas at standard temperatures and pressures, a mole of gas occupies a fixed value. That's true for all gases as long as they're at standard temperature and pressure. And the temperature for standard temperature and pressure is, oh man, I better be right about 0 degrees Celsius. I always have to double check to make sure it's not 20. I think it's 0 degrees Celsius and 1 atmosphere, ATM, of pressure, which is about the level of pressure you feel from the atmosphere when you're at ocean level. Anyway, provided those conditions are met, a mole of any gas occupies 22.4 liters. So 22.4 liters for every 1 mole. Or it's 1 mole for every 22.4 liters. Now, while these are all example molar mass, example density, example molarity, this is a specific value. This is not ever different for a different gas. All right, and lastly, molar ratio. So this applies when we have a reaction that we're aware of, and we're concerned about maybe some ratio of one reactant to another reactant. So an example could be, I think we use lithium and bromine as a reaction, which makes lithium bromide. However, bromine is a diatomic gas. I guess it's actually diatomic liquid at room temperature, but nonetheless it's diatomic, which is our concern. And so this is no longer balanced, so we need 2 of these guys. And if we have, okay, 2 there, then we need 2 lithiums. All right, and so another way you might convert is you might say, well, for a mole of bromine, how many moles of lithium do I need? And the answer would be 2. And you express that by saying for 1 mole bromine, you would need 2 moles lithium. Or vice versa, 2 moles lithium for 1 mole Br2. All right, now with that out of the way, let's start with some practice problems. All right, so we went over this idea that Maya isolates a mystery substance in a lab, and she doesn't know what it is, so she tries to identify it in some way. So she knows that the sample weighs 20.4 grams. It also occupies a volume of 45.65 mils. The question is, what's its density? Okay, well, it's pretty straightforward. Density is a measure of mass over volume. Okay, so actually to find the density, it's a very simple calculation. We just divide the mass of her sample, 20.4 grams, by the volume it occupies, 45.65 mils. We just get some fraction out of that. We have 20.4 divided by 45.65. And how many sig figs do we get? We get 3 here, 4 here, so we need the fewer number of sig figs. So we can say we are only going to have 3 significant figures here for 7 grams per mil. All right, pretty straightforward there. We're going to get more engaging soon, hopefully. All right, so we got granite has a density, so we're given a density, 2.671 kilograms for every liter. And the chief in Squamish is made of granite and has a specific volume. The question is, what's its mass? Okay, well, just like we've been doing in previous questions, we want to start with whatever we know that's specific to the example we care about. So in this case, we are told the volume of this object is 7.2 times 10 to the 10 liters. So that's about 10 billion, between 10 billion and 11 billion liters, which is plenty of liters, I think you'd agree. All right, and so we need to convert that because we're asked for mass. We need to somehow turn our unit of volume into unit of mass. To do that, we're going to use a density, and that's a conversion factor, as we covered earlier. And so we can choose whether to arrange it as 2.671 kilograms for every liter, or 1 liter for every 2.671 kilograms. So we're going to choose which one is appropriate in this place. And in this case, we want the units of liters to cancel out, and that occurs when another liter is placed diagonally below it. And so we're going to choose this conversion factor, which puts 1 liter on the bottom, and the 2.671 kilograms on the top. Okay, great. So liters cancel, and this shows by the arrangement of this conversion factor that we're just multiplying these two values. So we got 7.2, weird, okay, 7.2 power of 10, so this means times 10 to the power of 10. We're going to multiply that by 2.671, and that gives us a value. It's 1.9, wait, how many sig figs do we get? Just 2, okay, 1.9 times 10 to the 11 kilograms, which is about 100 billion kilograms. All right. So let's see what else we got here. Moet, he's got a pocket 160 dimes. Okay, they weigh 339.2 grams, and occupy 38 mils of space. And we want to know what the density is. Well, density is an intrinsic property of these metals. That's the word we use, intrinsic. In other words, it is not going to change with how many of them you have. This is an irrelevant value. It doesn't actually matter that he has 160 of them. Really, it matters that he just has some mass that occupies some volume, and that's sufficient to give the density. And that'll be the true density of 1 dime, it'll be the density of 10 dimes, or 160. So all we have to do is answer that density is mass over volume. So it is 339.2 grams, divided by 38 milliliters of space. And we get 8.9, around 2 decimal places, pardon me, 2 sig figs, because at 38 mils. Okay, so that means 8.9 grams per mil. Which, as we saw earlier, is actually the density of nickel. And that's because dimes are made of nickel, oddly enough. All right, so moving on. We've got density of table sugar, sucrose, is 1.59 grams per mil. Question is, how much volume will a bag that weighs 1 kilogram take up? Again, we always start with the specific value, 1 kilogram. We're going to say, okay, we're going to turn that into a volume. Our conversion factor in this case converts grams into volume. But we have kilograms. So actually I'm going to set up a conversion factor that converts kilograms into grams. I know that 1,000 grams is 1 kilogram. Kilograms will end up canceling out diagonally. And then I want to use this conversion factor to convert into volume. This says 1.59 grams is equivalent to 1 mil. I want the grams to cancel out, so I'll put them down here. There's 1 mil above. Grams will cancel. All right, and so this says that we just multiply across, but we have a couple of ones. So we got 1,000, which is going to divide by 1.59 grams. And we find that table sugar, a kilogram of it, will occupy, wait, how many sig figs do we get? Actually, just 1, technically. If I wrote this question again, I probably would have called it a 1.0 or 1.00 kilogram bag, so that was actually a bit of my fault. So you may have calculated this as a value, but maybe I'm going to write that in here. Mils per gram, which rounds to 600. Oh wait, what am I doing? Mils. So that's a little bit more than half of a Nalgene water bottle, because a whole water bottle is 1,000 milliliters, or a liter. All right, last we got this question about the sun. Okay, it's got a density of 1.410 kilograms for every liter, and the volume of the sun is 1.4 times 10 to the 30 liters. And then the question is, how much does it weigh? So we start with, okay, 1.4 times 10 to the 30 liters. And we're going to use our conversion factor here. We're going to convert liters, volume, into mass. And to do that, we're going to need liters on the bottom. So our kilograms are going to go on top. 1,410 kilograms. And when we do so, 1.4 times 10 to the power of 30 times 1.410, I get 1.974 times 10 to the 30 kilograms. However, that needs to be rounded, and it gets rounded to, 2.0 times 10 to the 30. Kilograms. And that's the mass of the sun. Okay. So moving on. Previously, I've been going through the examples at the beginning of the practice questions, and that's because Mac and Maya have been out of class, and they weren't there for those. But we're going to be going over these when we come back from Malibu on Monday. So I'm going to skip these, but I'm going to do the practice questions here so that they're all in one video, easily accessible. All right. So this is a section on molarity, concentration of solutions. And so let's start with question 4 here. It says the ocean contains 28 grams of table salt, sodium chloride, in every liter. The question is, what's the molarity, the concentration of ocean water? Okay, well, to do that, you just divide the solute. So molarity, just to remind us, so it's a capital M. It's a symbol, the unit rather we use, which means moles per liter. So every time you see capital M, you think moles per liter. And I would encourage you, every time you see it, to write moles per liter instead of M. Replace it, rewrite it. All right, so we want the moles of sodium chloride for every liter. Okay, so we're told that we have 28 grams of NaCl. Great, but that's not extremely helpful because molarity is in moles per liter. We could express concentration in terms of grams per liter, but that wouldn't be the molarity. So we're going to need to first convert 28 grams NaCl into some number of moles of NaCl. To convert grams into moles, well, what are we going to need to do that? Grams into moles. What tells us about how many grams of a substance are in a mole of that substance? Well, it's the molar mass. So we're going to look for the molar mass of sodium. That's 23.0. The molar mass of chlorine, which is 35.5. So the molar mass of sodium chloride is, I already forgot what sodium was, 23.0. We don't need the 0.0 on a calculator. Calculator doesn't know the difference between that and 23. And we find the molar mass of sodium chloride is 58.5 grams per mole. Now, we can use that as a conversion to convert mass into a number of moles. We can say, well, we want grams on the bottom, 58.5 grams for every 1 mole. These grams cancel out. Now we have moles, and so what do we have? We have, what does that tell us? 28 divided by 58.5, and that gives us a value of 0. How many sig figs should we get? 2, I suppose, for 8 moles of NaCl in every liter, which is to say that the concentration of sodium chloride in water is 0.48 moles per liter, or 0.48 capital M. All right. Moving on. All right, so we got Coca-Cola. It's a 0.32 molar sucrose solution. Sucrose is a long organic molecule. And Mr. Tang drinks one 355 milliliter can every day. The question is, well, how much sucrose has he ingested over the course of an entire week? And how about a year? All right, well, where should we start here? Looks like we have lots of information. We know that Coca-Cola has a concentration. We know that we have a specific volume of Coca-Cola. And we're asked about how much sucrose has he ingested over an entire week. All right, and a year. How much sucrose? That's not a well-defined question. What do we mean, how much sucrose? How many moles of sucrose? How many grams of sucrose? That could be more specific. I think we should choose the most illustrative option. Most people don't know much about moles, and so if we can express in terms of grams or maybe kilograms, something people can understand, that might be a better option. So where do we start, though? We have so much stuff, so much information. But let's use our good rule of thumb, which says start with the thing that is specific to our example. And in this example, we're talking about a 355 ml can of Coke, as opposed to a liter of a can of Coke or something like that. So we should probably start with that volume. And then we'll see what we can do with it. Okay, so we have a volume. We also have the concentration of that, 0.32 moles for every 1 liter. That's moles per liter. I'll just write that on the side. And we also have a substance with a molar mass. Okay. Now, if we're not sure how to go straight from, say, milliliters into grams of a substance, because there is no way to do that, this is not a density situation. We're not asking how much a can of Coke weighs. We actually only want to know how much the sugar in the can weighs. So we've got to figure out how much sugar is in there. But as we've seen before, if we're not sure about our path, we should probably start by turning things into moles. And I know a way to convert the number of liters of your solution into moles of your solute, and that's with the concentration. We need a little mini step first, though, which you might have already done sort of in your head or what have you. But if we want to convert milliliters of Coca-Cola into moles of sugar, we need to first turn milliliters into liters because our conversion factor is in moles per liter. So I'm going to do that as a conversion factor and say, okay, well, 1 liter is 1,000 milliliters. They cancel out. And now we're talking about liters. So now I can start converting liters into moles, which I can do using this formula. Pardon me, this conversion factor. And liters will live on the bottom so they can cancel out. And now we have moles as our unit that we'll be dealing with. We can do the calculations afterwards. Now lastly, we want to maybe turn moles into grams. That's a useful value. You can figure out how many grams of sugar Mr. Tang ingests in a day. And then we can figure out how much per week or per year pretty easily, I would think you would agree. So to do that, we're going to need to some way to convert moles into grams. And maybe it's a good time, if we forget how to do that, moles into grams, to take a look at our conversion factors. What do we have here that we could play with? What do we see that turns moles into grams? That is molar mass. Molar mass is a conversion between the grams of a substance to the number of moles of a substance, or vice versa. All right. So to do this, we need to find the molar mass of sucrose, which is a little heavy. All right, so I know carbon has 12 grams for every mole, and so there's 12 of them, so that's 12 12s. And I'm going to add 22 ones because I know the molar mass of hydrogen is 1. And I'll add to that 11 sixteens. And we get the molar mass of 342 grams per mole. I'll write that down here. And so if I want to convert moles into grams, I can just strictly do a multiplication here. I can take the mole on the bottom and the 342 grams on the top. Okay. All right, and now we've turned everything into grams, we're happy, and now we just have to punch this up into a calculator. So we multiply all the things across the top, and we divide by any terms we find on the bottom fraction. So 55 times 1 times 0.32, oops, times 342 divided by 1,000. So we get, there's about 38 grams, or 39 grams, of sugar, sucrose, in a can. So that means for a week, Mr. Tang ingests, it looks like 272 grams of sugar. 272 grams of sucrose. Actually, that should be only 2 sig figs, so let's call it 270 grams of sucrose a week. And I'm going to go back to that value of 39, so I'm going to divide by 7 again. So it's in my calculator, and multiply it by 365 to find the amount in a year. Looks like there's 14,000 grams, which I'm going to say is 14 kilograms. All right, two more. So you need to make 100 mils of a 0.300 molar solution of sodium hydroxide. Okay, so let's take a second to read that more carefully. If you need to make a certain volume of a solution that also has a certain concentration of sodium hydroxide in this case, well, to do that, we know we're probably going to need about 100 milliliters of water. The question is, well, how much of our solute, our NaOH, are we going to need to add so that overall, when we're all said and done, we have the right concentration? Okay. Well, here we should probably start again with a thing that is very specific to our case. We need exactly 100 milliliters. I'm going to start there. And as we saw before, it's actually going to be useful for us to turn those milliliters into liters. So we're going to do the same thing we did before. All right. Now, it's going to look like a very similar calculation as we did before. We convert into volume, and now we need to convert from volume into, looks like mass eventually. We can't go straight from volume into mass, and so we're going to use our concentration here. Okay, that's 0.300 moles for every 1 liter. That's what that says. That'll convert our liters, our volume, into, now we're talking about moles. If we're going to ask about moles, we're going to ask about mass, and so we need to convert from moles into grams. Again, we're going to need the molar mass of sodium hydroxide. Now, I've seen you guys are pretty good at doing that yourself, so I'm just going to read it out loud what I'm doing. So that's 23 for sodium. I'm going to add to that 16 grams per mole for oxygen. I'm reading off the periodic table, and 1 for hydrogen. It gives us a molar mass of 40 grams per mole. And that will allow us to convert 40 grams for every 1 mole. Okay. So we find, oh, and that's going to tell us the number of grams, the mass, but it won't tell us the number of molecules. So I think maybe we'll calculate this first. So we got 100 times 0.300, which is really just 0.3, times 40. And we'll divide that by 1,000. Looks like we need to measure out about 1.2 grams. That's not an answer for how many molecules, though, so we need 1.2. So that's some number of molecules, probably a lot, actually. And to do that, we need to convert from moles into molecules. So, where am I going to write that so it's not going to take up a ton of space? Yeah, I would say this is not typically sufficient space for you to solve these problems. I would advise you to do it in a notebook or something like that. I think I'll write it up here. So for how many molecules, we'll put a little arrow and say, okay, well, for the number of molecules, that's going to be pretty much the same calculations, but I need molecules, I'm going to need Avogadro's number, and that converts molecules from moles. So I need to go back to the mole stage in my calculation. So I'm actually going to write out those steps again. 100 mils times 1 liter for 1,000 mils times 0.300 moles for 1 liter. Now, I know the number of moles I have. I can convert that into molecules, which is 6.02 times 10 to the 23 molecules over 1 mole. And I'll find out what we get here. 100 times 0.3 times 6.02. That's divided by 100,000. And we get 1.806 times 10 to the 22 sodium hydroxide molecules. Okay. Last question for molarity. Okay, so if you want to make a float tank, you need to add 1.3 kilograms of magnesium sulfate for every liter. Okay, and the question is, well, what's the molarity of the tank? Okay, so to do this, we're going to need to find, so if we're asked for the molarity, what is the molarity? Molarity means moles per liter. We need to find the number of moles for every 1 liter. And we're not told, we're told how many kilograms there are for every liter. So actually we're not too far off. We can figure out a way to convert mass into volume, mass into moles, because we already have the volume of 1 liter. Well, then we should be good. Okay, I want you to pause the video now if you weren't sure about how to do this. See if you can think about what conversion factor is going to help us convert the number of kilograms of magnesium sulfate into moles. So we're going to need the molar mass of magnesium sulfate. So magnesium's at 24.3 grams per mole from the periodic table. Sulfur is what, 32.1. And I've got 4 oxygens. I know oxygen is 16. I know 4 16s is 64. So I'll add those together. We have 64 plus 32.1 plus 24.3 and that gives us 120.4 grams for every mole. All right, so that should allow me to convert 1.3 kilograms into moles. So first I'm going to turn these kilograms into grams. I know 1,000 grams are in a kilogram. And now I need to cancel out those grams. I'm going to take the 120.4 grams on the bottom and 1 mole on the top. And that gives us 1.3 times 1,000 and divided by 120.4, and we get 10 point, wait, how many sig figs? Oh, just 2 really, okay. It should be 11 moles. So 11 moles of magnesium sulfate for every liter. So we get a molarity, or concentration, of 11 moles per liter, or 11 molar. All right, we'll call the video there.